because today we're diving headfirst into analytic number theory. We're looking at a paper that's using this incredible tool called the ANTEDB, the Analytic Number Theory Exponent Database.
Yeah.
And get this, they're using it to push the boundaries of what we know about zero-density estimates.
Yeah, the ANTEDB is really a game changer. It's like, think of it as a massive interconnected web of all these crucial exponents in number theory.
Okay,
And what makes it so powerful is that when you update a bound on one exponent,
right.
it ripples through the entire system, optimizing others in a chain reaction.
Okay, so why does any of this matter? Are we just playing with numbers here?
Not at all, not even close. These exponents are, they're the keys to unlocking deeper truths about the Riemann zeta-function.
Right.
And understanding that function has huge implications for everything from the distribution of prime numbers to potentially even physics.
Wow, okay, so let's back up for a second though. The paper focuses heavily on something called exponent pairs.
Right.
What are those and why are they so important in this whole puzzle?
So an exponent pair written as k
Okay.
isn't just any pair of exponents.
Right.
It's a specific concept in analytic number theory that helps us control the growth of these things called exponential sums.
Okay.
And these sums, they pop up everywhere when you're dealing with the Riemann zeta function.
Okay.
They're notoriously difficult to handle, but exponent pairs give us a way to tame them.
Okay, so how do you even find these special exponent pairs? Do mathematicians just pull them out of a hat?
Well, there's a very specific process. Imagine a triangle defined by some inequalities.
Mm-hmm.
Each point within that triangle represents a potential exponent pair. We have these mathematical moves called A, B, and C processes, which let us take an existing pair and transform it into a new one, all while staying within the bounds of our triangle. It's like strategic maneuvering in a game.
Wait, so it's a game with rules.
Absolutely, yeah. There's even this almost magical move called the Sargo's D process.
Okay.
It's a way to tweak exponent pairs while nearly perfectly preserving their special properties.
Wow.
And the whole game is driven by this big unsolved problem called the exponent pair conjecture.
Okay, so what does this conjecture say?
It predicts that a much wider range of exponent pairs exists than we currently know.
Okay.
And if we could prove it, it would be a huge leap forward in our understanding of exponential sums and the zeta function.
So where's the ANTEDB fit into all of this?
This is where it gets interesting.
Okay.
The researchers used the ANTEDB to discover four entirely new exponent pairs.
Wow.
They did this by cleverly combining existing knowledge and computing a special kind of shape called a polytope.
Whoa, so they essentially found new moves in this mathematical game using computational power.
Exactly, yeah. And that's just the tip of the iceberg. These new pairs have ripple effects throughout the ANTEDB,
Right.
leading to improved estimates in other areas.
All right, I'm definitely hooked. But before we go any further, can you explain what this duality thing is between exponent pairs and this function you mentioned earlier?
Yeah, it's a crucial concept. So you see, each exponent pair doesn't just give us one bound on the growth of exponential sums. It actually provides a bound for a whole range of values represented by this function.
Okay.
It's like a single key unlocking multiple doors.
Fascinating. So they found new exponent pairs which influence this function, but how does that connect to the whole zero density estimate thing we talked about at the beginning?
We're getting there.
Okay.
But first, we need to talk about another crucial piece of the puzzle, something called large value theorems.
Ooh, intriguing. This is where it gets really interesting.
Yeah.
Lay it on me. What are large value theorems all about?
Large value theorems, they're all about finding those moments when the Riemann zeta function gets unusually large, those spikes.
Right. And why are those spikes so important?
So think of it like this. The Riemann zeta function is this incredibly complex landscape.
Okay.
And we're trying to map it out, understand its peaks and valleys, the zeros of the function,
Right.
those points where it equals zero.
Yep.
They're like the deepest valleys. They're incredibly important for understanding the distribution of prime numbers.
Okay, I see. So these large values are like landmarks that help us navigate this complex landscape.
Exactly, yeah. And large value theorems give us tools to measure and analyze these landmarks.
Okay.
They use parameters like n, t, and v
Right.
to characterize the size of these large values and how frequently they occur.
Okay, so N, T, and V are like our measuring sticks.
Precisely. Now there's this special exponent called LV
Okay.
that quantifies how big the set of frequencies exhibiting these large value patterns can be.
Right.
It's a crucial ingredient in many of the results we're discussing today.
It sounds pretty abstract. Is there any way to visualize how this LV exponent works?
One way to think about it is through Huxley's subdivision method.
Okay.
It's a technique that lets us break down the problem of finding large values into smaller, more manageable pieces.
Okay.
And this method can be expressed as a functional inequality for LV,
Right.
which makes it easier to manipulate mathematically.
So it's like breaking a complex puzzle into smaller pieces that we can actually solve.
A good analogy. Now remember that exponent hair conjecture we discussed earlier.
Right, right.
Well, there's a similar conjecture in this realm called the Montgomery conjecture.
Another conjecture. You mathematicians love your conjectures.
They guide our exploration.
Mhm.
The Montgomery conjecture essentially says that we have a pretty good grasp on the maximum size these large value patterns can reach. Proving it would be a major milestone.
So it's like saying we've outlined the boundaries of this landscape, but we still need to fill in the details.
Exactly. Yeah, we have theorems like the L2 mean value theorem and the Bergen large values theorem that provide partial progress towards this conjecture.
Okay.
But a complete proof remains elusive.
So mathematicians are still working on conquering that peak, so to speak.
Absolutely, yeah. And the techniques they're developing along the way are incredibly insightful. For example, one trick is to raise a Dirichlet series to a power.
Okay.
This extends the reach of our large value theorems, allowing us to explore even more of the Riemann zeta-functions landscape.
Wait, what's a Dirichlet series? Should I know that?
Don't worry too much about the technical details.
Okay.
Just think of it as another tool in the mathematician's toolkit for analyzing the zeta function. The important thing is that by raising it to a power, we expand the range of frequencies.
Okay.
Where we can apply our large value theorems. It's like getting a more powerful telescope
Right.
to see further into the universe.
I like that analogy.
Right.
So we've got these large value theorems,
Right.
these conjectures guiding our search, but how does this all connect back to those zero density estimates we talked about at the beginning?
That's the truly remarkable part.
Okay.
It turns out that large value theorems can be used to deduce zero density estimates.
Wait, so these spikes we're talking about, those large values, can tell us something about where the function goes to zero? That's wild.
It is, yeah, and it works the other way around too.
Wow.
Under certain conditions, zero density estimates can imply large value estimates.
Really?
It's like a two-way street between these seemingly separate concepts.
So it's all connected. But before we dive into those connections, remind me again, what exactly is a zero density estimate?
It's all about understanding how many zeros of the Riemann zeta function can be packed into a specific region of the complex plane.
Okay.
Imagine a map of this complex plane.
Okay.
Where each zero is marked with a pill.
Right.
The zero density estimate tells us how densely these pins are clustered together.
So it's like a population density map, but for the zeros of the zeta function.
Exactly.
Okay.
And just like understanding population density helps us understand things like resource allocation and urban planning. Understanding zero density helps us understand fundamental properties of the Riemann zeta function.
Right.
And ultimately the distribution of prime numbers.
Okay, I'm starting to see how it all fits together.
Yeah.
But we haven't talked about the ANTEDB in a while. How did the researchers use it to make progress in this area of zero density estimates?
They used it to leverage the power of large value theorems.
Okay.
By cleverly combining existing knowledge and applying powerful computational techniques.
Right.
They were able to derive new and improved zero density estimates.
Okay.
Some of these estimates even surpassed long-standing classical bounds like Ingham's and Huxley's.
So they're not just refining our map of the zeta function, they're redrawing entire sections of it.
That's incredible.
But before we get too carried away, let's break down what what exactly a zero density exponent is.
Okay.
And you mentioned something about the density hypothesis earlier.
Right.
What's that all about?
The zero density exponent, denoted by A's,
Okay.
is a measure of how tightly packed those zeros can be in a specific region of the complex plane.
Right.
The smaller the value of A's, the tighter the packing.
Right.
And the density hypothesis is a conjecture that predicts the best possible bound on asses. If we could prove it, it would be a major breakthrough.
Okay, so we've got these new zero density estimates, this density hypothesis hanging out there. Anything else we should know about before we move on?
There's one more fascinating concept that this paper explores: additive energy.
Additive energy. Now you're just messing with me.
Yeah.
But all right, I'm game. Hit me with it. What is additive energy, and what does it have to do with the Riemann zeta function? Okay, my brain is officially fried. We've gone from exponent pairs to large value theorem to zero density estimates, and now additive energy. Like, I feel like we're going deeper down the rabbit hole with every concept.
Yeah, it's true that additive energy can seem a bit abstract at first,
Right.
but it's a fascinating concept that connects to the Riemann zeta function in a very surprising way.
Okay.
So think of it like this. We've been focusing on the size of these large value patterns.
Okay.
But what about their structure?
Okay.
Additive energy gives us a way to measure how organized or how structured a set of numbers is.
Okay, so how do we apply that to the Riemann zeta function? We're not talking about arranging numbers in a neat little row.
Right. We're specifically interested in the structure of the imaginary parts of the zeta function's zeros.
Okay.
Remember those pins on our complex plane map?
Right.
If those pins representing the imaginary parts
Okay.
are clustered together in a very specific, organized way, it tells us something about the underlying structure of the zeta function itself.
So it's like looking for patterns within the patterns. We're not just interested in where the zeros are, but how they're arranged relative to each other.
Exactly. Yeah. And just like with large value theorems and zero density estimates,
Right.
we have special exponents that help us quantify this additive energy.
Okay.
So we have LV and AS,
Okay.
which are the energy aware versions of the exponents we've already discussed.
So these new exponents capture not just the size of the large value patterns, but also the way their imaginary parts are structured.
Precisely. Yeah. They allow us to explore the interplay between the size and the structure,
Right.
leading to even deeper insights into the zeta function.
Right. So where do these large value energy regions E and Is come into play? They sound pretty mysterious.
Think of them as special sets that contain a treasure trove of information about the additive energy and something called double zeta sums associated with these large value patterns.
Okay.
Mathematicians explore these regions to uncover new bounds and relationships, pushing the boundaries of what we know.
So they're like hidden chambers within the already complex world of the zeta function. And I'm guessing the ANTEDB is involved in exploring these chambers?
Absolutely, yeah. The ANTEDB has been instrumental in proving new theorems that connect the size of large value patterns to their additive energy.
Okay.
One key result is Theorem 63, which is sometimes called the Heath-Brown relation.
Okay, so what does this Theorem 63 do?
It establishes a powerful link between the size of a large value pattern and its additive energy.
Okay.
And this connection has opened up new avenues of research, allowing mathematicians to leverage knowledge about one to gain insights into the other.
It's incredible how everything seems to be interconnected in this world.
Yeah.
But before we get lost in the details, remind me again, why should I care about additive energy? How does it connect to the big picture of the Riemann zeta function and number theory in general?
Well, remember that the Riemann zeta function is deeply connected to the distribution of prime numbers, those fundamental building blocks of all numbers.
Right.
Understanding the structure of the zeta function's zeros gives us a powerful tool for understanding prime numbers.
Okay.
Additive energy provides a new lens through
Okay.
which to view this structure, potentially leading to breakthroughs in our understanding of prime numbers and in their distribution.
So it's like we're adding another dimension to our map of the zeta function. We're not just looking at points on a plane anymore, but at the complex relationships and structures between those points.
Exactly. Yeah. And the ANTEDB project has demonstrated just how powerful this new lens can be.
Okay.
They were able to derive a whole family of new bounds
Wow.
on the additive energy of the zeta function zeros, covering different ranges of values for that crucial sigma parameter.
So they're not just adding detail to the map. They're creating a whole new layer of understanding.
Precisely. Yeah. And this is just the beginning.
Right.
Additive energy is a relatively new area of research.
Hmm.
And the ANTEDB is helping mathematicians explore its potential in a systematic and powerful way.
This entire deep dive has been a whirlwind of mind-bending concepts. We went from exponent pairs to large value theorems to zero density estimates and now additive energy. It's incredible how the ANTEDB has connected all these seemingly disparate threads into a cohesive picture. But before we wrap up, I have to ask, what are the biggest takeaways from this deep dive? What should our listeners be pondering as they go about their day?
Well, I think there are a few key things to consider.
Hmm.
First, the ANTEDB project has demonstrated the incredible power of systematizing and connecting mathematical knowledge
Right.
by creating a centralized database of exponents and their relationships. Mathematician can leverage existing results in new and unexpected ways.
It's like having a superpowered research assistant that can instantly cross-reference and analyze all the relevant information.
Exactly. Yeah. And that leads to the second takeaway.
Hmm.
Collaboration is key. The ANTEDB fosters a collaborative spirit
Right.
by making it easier for researchers to build upon each other's work.
Right.
This paper we've been discussing is a testament to that, leveraging results and techniques from many different areas of number theory.
Absolutely. Yeah. And finally, this paper shows us that there's still so much more to discover.
Right.
Additive energy is a relatively new concept, and the anti-B is helping mathematicians unlock its potential.
Right. And it's not just about the Riemann zeta function,
Right.
the ANTEDB approach, this idea of systematizing and interconnecting mathematical knowledge could be applied to other fields as well.
So as we leave our listeners with this final thought, I encourage everyone to embrace curiosity, to explore the interconnectedness of knowledge, and to appreciate the beauty and power of mathematics. Who knows what groundbreaking discoveries await us just around the corner. Thanks for joining us on this incredible deep dive. We'll see you next time as we explore another fascinating frontier of knowledge.
Oh, hey, welcome. What's up?
Absolutely. Let's unpack zero density estimates a bit more.
Yeah, that's a great question. We've touched on it, but let's really dig in.
So think of the Riemann zeta function and all its zeros.
Right, those points on the complex plane where the function equals zero.
Yeah, the zero density estimate is all about figuring out how many of those zeros there are in a given area.
It's like estimating population density, but for these mathematical zeros.
Exactly. And the density hypothesis says that the zeros can't be too tightly packed together.
Right, it predicts a maximum density, which, if true, would be a major breakthrough.
And this connects to the large value theorems we talked about earlier.
Yes, those large value theorems, they give us a way to estimate these zero densities.
So when the zeta function spikes high, it also tells us where the function goes to zero.
It's a fascinating relationship between these peaks and valleys.
And the ANTEDB has helped mathematicians find new relationships between these concepts.
Exactly. So by systematizing all of these number theory results.
Right, we can find new and unexpected connections.
And this approach has even improved upon some long-standing bounds.
Like some of those classical bounds from Ingham and Huxley.
Yeah, the impact of the ANTEDB is pretty significant.
So in short, a zero density estimate is about understanding the distribution of these zeros.
Yeah, and the density hypothesis is a conjecture about the maximum density they can have.
And these are very important for understanding prime numbers.
Precisely. Does that help clarify things a bit?
I hope so. All right, so where were we? Yes, we had just wrapped up the main points of the paper, didn't we?
Yeah, we were just about to leave our listeners with some final thoughts.
So as we were saying, the NTB shows us the incredible power of systematizing and connecting mathematical knowledge.
Right, and that's not just applicable to the Riemann zeta function.
Absolutely. This idea could be used in other fields too.
And it highlights the importance of collaboration.
Yeah, building upon each other's work is essential for progress.
And of course, it reminds us there is still so much more to discover.